Okay, guys, unfortunately, I'm kind of sick today, so I don't know if I'll get much done. Um, the next one here, um, the following problem is, oops. The following problem considers the scalar form of Coulomb's law, which describes our first given. It is given by this equation. Okay, yeah. To simplify the calculation of a model with many interaction particles, after some threshold value r equals r, we approximate f as 0. Explain the physical reason behind this assumption. But basically, the idea is the f becomes too small. It's quantum effect, other things like that, but it becomes too small, less than what can be measured, we could say. Insignificant, irrelevant, negligible, etc. What is the force equation? I guess we could say it's force for radius r will be Ke Q1 Q2 over r squared. That's when r is less than r, and then 0 when r is greater than or equal to r. Okay, evaluate the force. Okay, let's try and type this in if we can. Okay, 8.988 times 10 to the power of 9. That's the K. Assuming 2 protons with a charge magnitude of that. Okay, evaluate the force using Coulomb's law and our approximation, assuming 2 protons. Okay, so 1.6022 times 10 to the power of minus 19. Are 1 meter apart. And also assume r is, oh, hang on, if I wrote this backwards, I just realized something here. Yeah, okay. And r is less than a meter. Oh, I understand. Also assume that r is less than 1 meter. How much inaccuracy does our approximation generate? Is our approximation reasonable? I'm not quite sure what's going on here. Okay, anyways, let's see. Okay, 1 meter apart, so that makes the r squared 1. That's easy. So it's just going to be K, which is 1, times Q, times Q. So that's how much force should equal 0 newtons, but the formula, if we don't use this model, but without the or, then that would mean the force would equal 2. We'll just do 3 significant figures. I'll write the full number: 2.307 259902. Now, I need to read this again because I think there's something not clear here. The following problem considers the scalar form of Coulomb's law, which describes the electrostatic force between 2-point charges such as electrons. It's given by this equation where K is Coulomb's Qi, the magnitude of the charge of the two particles, and the distance between the two particles. Simplify the calculation of a model with many interacting particles after some threshold value or equals, or we approximate F as 0. Explain the physical reasoning behind this assumption. What is the force equation? I'm not sure what they mean here. I thought they meant what is just the equation with the improvement here. Evaluate the force F using both Coulomb's law and our approximation, assuming 2 protons. Okay. Yeah, so like, yeah. So this is are we calling the or equal or with the approximation? Yeah, this is with the approximation. And then this is without. Okay. So sorry. Right. Okay, I think that's what they are looking for. It's 0 force or that tiny force. Okay. Is there any finite value of or for which this system remains continuous at or? No, we can't. Because if we look at the graph, what's going to happen is we'll get a graph like this. And it's always going to jump. There'll always be a jump. Okay, that's a bit of a messy question. 169, instead of making the force 0 at or, instead we let the force be 10 to the minus 20. Assume 2 protons which have magnitude of that and Coulomb's constant at that. Is there a value of or that can make the system continuous? If so, find it. Okay, let's clear this off. And at least with 169, there's going to be an answer at the back. So can we find that answer? Okay, assume 2 protons which are magnitude at. Yeah, okay, so we want a point where K, Q1, Q2 over or squared at the point or, that's equal to 10 to the minus 20. So the or will be root K Q1 Q2 over 10 to the minus 20. So that would be the point where we could make it at that point we could make it continuous, at least the approximation, and no jump discontinuity. So if we just type in square root 10 power, let's just say minus 20, not minus 2. Coulomb, and then is it the same again? Have a look. 1.6022. Yeah, same again. Okay. Okay. Yeah, okay. So we could go with 0.000151. Well, I should go with the same number of significant figures, really. 1, 2, 3, 4, 5, but there's a root, so I'll go 6. 1, 2, 3, 4, 5, 6. So 897 meters. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll say that's 151,847 nanometers. That's a 9,7. Sorry. 151,897. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay. Okay. That was 169. Okay. Okay, let's have a look now. Just jump down to answer for 169. 1519. Yeah, that's what we have. Okay. Determine the value in unit of K given that the mass of the rocket is 3 million kilograms. Okay, I think unfortunately I'm gonna have to stop there because I don't feel too well, and I was my intention to finish this, but I don't think I can. So we'll leave it there, and I'll see you next time.